Hello. Today we are getting ready to look at unit number 2. Unit number 2 is called Reasoning and Proof, and it is really the beginning of discussing this idea of proof in geometry. So we are going to begin with analyzing logic and learning about different types of logical statements. And we will end the unit starting to look at properties, more theorems, and begin writing proofs. All right, so section 2.1, use inductive reasoning, we are going to start with. So if you want to get to page 3, I do have some definitions I'll have you write out. To start with, I usually try to leave the learning targets at the top. I think you'll find that today is about patterns, and you'll see some similarities between science class and what we're talking about in this unit as well. So, all right, our first definition, conjecture. A conjecture is an unproven statement that is based on observations. An unproven statement that is based on observations. So a conjecture is just something you say, or something you notice happening, you see a pattern happening, and you make a conjecture. So for example, if Monday seems to always be sunny, so let's say the last 3 Mondays have been sunny. So my conjecture might be that it is sunny on Mondays. So it's not necessarily a proven statement, but it's just based on my observations. Okay, inductive reasoning. So inductive reasoning is the process of looking for patterns and making conjectures. We do this on a daily basis. We notice patterns and we make conjectures or statements about whether that's going to keep happening. So I've got 1, 2, and 3 listed out because that's kind of the order that we logically go through things. So number 1, what we usually do is we look for a pattern, and we're going to do that here as we work some examples. Number 2, we make a conjecture. And then number 3, we verify that conjecture, which could be true, but it may not be true 100% of the time. So that's why it's an unproven statement. Third item, counterexample. A counterexample is simply an example to show something's false, or to show a conjecture is false. So back to the example of every Monday it will be sunny. So a counterexample would be that we have a Monday happen and it isn't sunny. So if you can come up with one counterexample, then you have just disproven your conjecture. So these are the 3 items we're going to focus on today. So if you need to pause this to catch up, go ahead and do that. All right, let's look at some patterns here. So the very first part of inductive reasoning is starting with some basic patterns. So on these 2 examples, we are going to sketch the next figure. So we are going to notice what's happening in the prior 3 figures, and then we're going to assume that's going to happen in the next one. So I can see that the main difference is this dot seems to be moving around the circle. So it moves to the right, and then it's in the upper right section, and then it moves down. So I am going to use inductive reasoning to say, let me go ahead and add this, that the dot seems like it's going a quarter of a turn. So it appears like it will end up down there. Okay, so do the same on number 2. Go ahead and sketch the next figure just based on the pattern you're observing. Okay, so I am observing that the 2 dots seem to be traveling in a counterclockwise fashion, and so they should land at the top here. So that's inductive reasoning, something that you do on a daily basis. So let's keep going with patterns and describe number patterns next. Number 3, describe the number pattern in the numbers 2, 8, 32, 128, etc., and write the next 3 numbers in the pattern. So when we describe number patterns, we try to say things like it's adding 5 every time, or it's dividing by 3. We're doing some sort of numerical pattern. Sometimes it's not as easy as it's adding a number every time. You might have to describe it differently. So take a look at what are some observations you make here? I see that these numbers are growing really fast. So like I might start by saying, well, maybe between 2 and 8, maybe it's multiplying by 4. So, okay, it seems like it's multiplying by 4 here. So let's check the other one. So if I do 32 times 4, okay, I get 128. So my pattern is multiplying by 4, or I'm going to just go ahead and put that sign right there, multiplication or multiply by 4. And so let's do the next 3 numbers it says. So 128 times 4. So it looks like I have 512, 2048, and then finally 8,192. So if it wouldn't have held true where it was multiplying by 4 every time, then I would have, I guess, continued to look for a different pattern. Okay, do number 4. Go ahead and stop the video here and describe your pattern and go ahead and give the, looks like we're just doing the next number on this one. So here's an example where it's a little harder for me to describe it by just multiplying by a number. You might be able to come up with a pattern that does that, but it's okay to notice. So 17 to 15, it's going down by 2. 15 to 12 going down by 3, and then down by 4. So I'm going to just kind of jot down like this. I'm going to say -2, -3. So, I mean, I guess if we wanted to be a little bit more elaborate, we could say the pattern, well, it's starting by decreasing by 2, but then it's decreasing by 1 more integer every time, or you could come up with some sort of way to say that. So the next number, I'm going to have to go down by 5. So it looks like I will have 3 as my next number. Okay, let's keep going. All right, number 5. 5, 6, and 7. So we are going to make and test a conjecture. So remember a conjecture is just an unproven statement that's based on what we observe. All right, so what we just did were number patterns. So this one says we are coming up with a conjecture about the product of any 2 odd integers. So product, you're thinking multiplication. So what I'm going to do is create at least 3 examples where I find the product of 2 odd integers and see what I come up with for my pattern. So I might just start with, I don't know, 1 and 3. So if I do 1 times 3, I get 3. It doesn't say they have to be positive, so maybe I'll try, I just did 2 positives. Let's do 1 negative and 1 positive. So I'm going to go with, let's do -1 again, and I'll do 5, +5. So that will give me a -5. And then I haven't done 2 negatives. Let's see if that, see what I get on that one. So how about maybe a -3, I don't know, and a -7. That would give me 21. So I am trying to write a conjecture about the products. So here are my 3 products, and I've got a variety of positive and negative. So based on my 3 examples, I see odd numbers here. I can't say that any of them they're not always positive or negative. So that's going to be my conjecture. My conjecture will be that the product of any 2 odd integers is odd. So we do want to write that sentence out as our conjecture. So the product of any 2 odd integers, is odd. Okay, so that is my conjecture. So it says to make and test. We're really testing it, and then we're making it. So I came up with my examples and then made my conjecture. Okay, you might try 6 and 7. So go ahead and pause the video, work out some examples. I would always stick with a minimum of 3 and try to come up with a variety, if you can, positives and negatives to help you arrive at your conjecture. Okay, I am looking at the product of an even and an odd. So again, I'm going to cycle through positive and negative. So even. So let's maybe do 2, 7 is odd, 14. And then I can work with maybe negative 4. That's even, but negative. Let's do a positive. So 5 is odd, negative 20. And then let's do 2 negatives like we did up here. So even and odd, so maybe like a negative 6 and a negative 9. So that gives me 54. 14, negative 20, and 54. So the first thing that jumps out at me is that they're even. Again, they're not always positive or negative. So that's going to be my conjecture, that the product of an even integer and an odd integer is even. Product of an even integer and odd integer is even. And I guess we could go on and say it is an even integer because I am getting integers here. Okay, number 7 is a little trickier. The sum of the first n positive odd integers is blank. So I'm going to write out some scenarios where I add together the first, and then n is just however many we're going to work with, 1, 2, 3, 4, 5, whatever. The first n positive, so I have to be positive and they have to be odd, of course, and integers. So let's start with, let's say, well, here's what I'm going to set it up as. If n is going to be the number of numbers that we're putting in the example. So if n is 1, this is a little bit harder because you just have one answer. The sum, of course, is just 1. Okay, but let's go on to 2. The first 2 positive odd integers. So 1 is odd, plus 3 is 4. Okay, so let's say, what if we have 3? What if n is 3, which means I'm adding 3 numbers? So, and they must be odd. So 1 plus 3 plus 5, that would be a 9. And then maybe let's just do one more. You can do as many as you want, but 4 of them. So 1, 3 plus 5, and then 7 is next. So that would be 16. All right, so we're looking at the number 1, the number 4, the number 9, the number 16. And there's kind of a pattern that I'm hoping jumps out at you. 1, 4, 9, and 16, those are perfect squares. So the way that what I can fill this conjecture in, and what I'm going to do is fill this blank in, the sum of the first n positive odd integers is, now I know it's a perfect square, but if you relate it back to the n, 1 perfect square is 1. 2 perfect square is 4. 3, 9, 4, 16. So if I take the number of numbers I'm adding and I square it, I'm going to get the sum. So if I extend this to 5, I should get 25 as my next answer. So the blank here is going to be n squared. So that's kind of a tricky one because you have to look for that pattern. Okay, I'm going to finish the last few examples in the next video. So if you want to stop here and then move on to the next one.